It's now my pleasure to introduce my friend Victor Yodaiken. He's going to talk about practical fault tolerance for time distribution in financial markets. Victor, the floor is yours.
Yes. Oh, right. Okay, so we went from pragmatic to practical. Oh, touch the microphone. All right. The microphone's on the wrong side for a left-handed person, though. It's discriminatory. Okay, so we went from pragmatic to practical. I'm going to talk about how we've provided fault-tolerant time in financial marketplace over the last 6 years. And unfortunately, I have a slide set that could have been updated, but I don't really like to talk from the slides anyway, so I'll improvise as we go along. All right, so the issue that we want to deal with is how do you actually have practical fault? Oh, I can look at it there. All right. You guys are advanced. The issue that you have in time delivery in financial networks particularly is it reliable? And what people are facing now more directly, many people are looking at, is if the regulators ask you, show us that this device that was trading at this time, that time-stamped a transaction at this time, was it really on time? Was your time accurate? You want to be able to show that, I was getting time from this clock, and this clock was actually accurate, and what happens if that clock broke? Well, then I switched over to another time. When we started into this field, I think partly because of the telecom basis, telecom has got extremely reliable equipment, really top-notch equipment. But in the financial markets, we're dealing with commodity networks, commodity parts, really complex networks that often fail. And you have a greater degree of both hardware and software failures that can interfere with the system. And so what we want to be able to do is when the regulator says to you, prove to us that you were actually said this happened at 12 noon and it really did happen at 12 noon, you can say, here's my primary clock, and it agreed with a secondary clock, or my primary clock failed earlier, but I failed over to a secondary clock. Okay, so one of the things that you started with when we looked at this market is that NTPD, which is the sort of old software that does NTP delivery, and PTP, neither of them provide a level of fault tolerance that meets the requirements of the market. And you can see that the PTP standard has evolved over time. The new PTP enterprise standard is a big step towards addressing this. But PTP originally was designed for an environment where failures did not have to be transparent, where you didn't have to automatically compensate for a problem in a clock. In fact, the clocks were considered to be the source of all truth. So the PTP best master clock algorithm, which is the foundation of how you pick a clock, PTP assumes that the clock knows. So the clock says, I am within 1 femtosecond of real true time, and the client, the slave, is required to believe that. And what happens if the switch in between, or a cable in between, or a GPS connection or something has failed and the switch doesn't know? You're out of luck. So what we wanted to do was to introduce techniques for compensating for that were outside of both of those protocols. NTPD provided a method of fault tolerance which was based essentially on averaging, on trying to aggregate together multiple time sources and produce a quality time source out of it. And that also is not appropriate for the financial markets for two reasons. The one is that simply aggregating these time sources often gives you a worse time source than any of the ones that you're aggregating. If two of them are out of sync and you're averaging that in with your one good time source, you're now automatically off sync. So basically it means that you have a failure model where any one of your sources failing causes your system to fail. The other thing is, and this is a big issue now for the regulatory compliance, is that method takes away from you the ability to track back where your source was, right? You have an NTP source that's blending in multiple time sources, and you then can't say, well, we had two of these time sources were GPS and one came from somewhere else, so where was our true source? How can we back it up? We don't know because there was some complex merging algorithm in the middle of it. So, what are we focusing on? We're dealing with commercial networks. They have a huge variation in network equipment. A lot of investment in that already. It can't all be thrown away and replaced with new stuff. Our points of use are standard computer servers. They're not specialized devices. We're running trading algorithms on high-end HP servers or Dell servers or something else. These are not special devices. Accuracy requirements can vary between hundreds of microseconds and sub-microsecond, depending on what we're doing. We have shared network systems for delivering time with very big difference from our old telco networks. We're now sharing the network between data and time packets, which causes all sorts of interesting features. And now we have all this other stuff that's coming in: cloud, big data, industrial automation. These are other areas where time synchronization is needed. And cloud is actually particularly interesting in financial markets now. But all these areas that are way outside of traditional telco that need reliable timing. So when we first described this in the 2011 talk that I gave at WSTS, plug for WSTS, I gave an example of how you do failover, a very simple example how you do failover in our system. And this is just a really dumb system where you're saying, I have 3 sources, and what I want to do, one of them is my highly reliable PTP source that I'm bringing in, and then I have 2 different NTP servers that I'm bringing in. And I just wanted to put in a correction from the perspective that we got from the last 2 talks. NTPD is a unreliable method of delivering NTP. It doesn't give you high accuracy. But NTP as a protocol is really very similar to PTP. And in fact, the NTP telco protocol is almost identical to PTP. There's nothing magical about it. You're just sending packets over a network. All the same challenges are there. So you can actually get very good accuracy out of NTP2. So what this is showing you is an example where we have a primary source and we're going to fail over in the order that we're given to secondary sources if we detect a problem, which is also an issue that we have to deal with. And you can see the kind of graph that we show you here. There's multiple NTP sources, and there's big differences between them because there's some offsets. Some of them are showing different times, but you can also see that they vary at various times. Some of them start bouncing up and down. Sorry, I need to have this thing follow me around. So you can see this one's bouncing up and down. There's a big variation at the end. I'm going to show you at the end a slide that shows, as Dr. Levine was showing, Google's bizarre approach to the leap second would mean that if you were following Google as your time source, you would be a half a second off for a significant amount of time because of their strange 20-hour slew. But if that was your time source, you would have no way to know that you were off. And so what we're showing you here is multiple time sources so you can compare them and you can say, wait a second, this is what I think is my primary time source. What's wrong? Why are we so far off with our other sources? All right, so what have we done over the last 5 years? I mean, we've been, in fact, this is what I don't like to tell our old customers, but in fact, we've been debugging software for 5 years on their systems. And finding out what works, what doesn't work, where the points of failure are, and they're often surprising points of failure. So we've had a protocol-agnostic multi-source, which is a big one. That was our initial choice. We said we want to be able to produce sub-microsecond time accuracy with both PTP and NTP, and we want to fail over between them, and we want to be able to use them to compare against each other. So that turned out to be a big win. Failover triggered by client analytics. What I mean by that is these devices that we have that are doing timing for us, that are running our algorithms, are incredibly smart devices. And people are running, 3.5 gigahertz multi-Xeon systems with enormous numbers of cores, enormous amount of memory. These devices have the ability to do analytics that tell whether or not the time sources that they're following are matching each other, and to detect anomalies in those time sources. So we've based a lot of the work that we've done on trying to make the end users, the clients, not just simple slaves, but actually very smart clients that are able to say, something is funny about one of my sources. I'm going to switch over to something else and document why they did it and when they did it. We have a single primary at any time, so we're not averaging together sources. And this is a point that Doug made. We're using the protocols for interoperability, not algorithm design. There is a lot of stuff in the NTP so-called kernel, which tells you how you should implement NTP. But we've kind of said we don't care about that. As long as we're doing the NTP packets, as long as everything is interoperable, we don't care. We will just drop David Mills' suggestions and make things work as accurately as we can. So, this works for GPS clock failover as well as client failover. What you're seeing here is multiple sources. One is a GPS source and 2 high-quality PTP sources, all within 200 nanoseconds of each other. It allows you to know with very high reliability that you're actually within time and to document that you're within that time. So I'm going to talk about some of the errors that we found over time in the system. The one that's not up here that is really my favorite one is we had a customer who was seeing one time source that was starting to wobble compared to another one in the same data center. And after much research, they found it was due to the fact that the cleaning shift that came in at a certain part of the day was parking a cart in front of the air intake of the rack, and the rack was warming up. I mean, this is something that you have to deal with. This is the kind of practical issue that there's no real way to design against it. You can only alert when something happens. We've seen GPS clocks that silently lost GPS and failed over to an NTP backup. We had one bank that had a GPS source that had for a period of at least several months been intermittently failing and calling up over a phone line to a source across the Atlantic it was getting NTP from. And they would see accuracy problems, but if you only had one time source, you weren't able to see that something funny was going on. Network security is the bane of the lives of people trying to deliver high-quality time often. It's common for them to say, I don't know what this NTP or this PTP protocol is. Parts of PTP protocol, there's 2 parts to the PTP if you do hybrid. It's very easy for some over-eager network security engineer to say, I don't know what those packets are, I'm going to cut them off. And unless you're alerting on the fact that not all of the protocol is operating, that there's a problem, or you're alerting on a comparison, there's no way for you to detect that. This is something that happened recently where there were some premature leap second clocks. Some of them were overeager, they jumped. Canadians, for some reason, have a particular problem with this. They really wanted it to be the leap second a lot earlier than it was. But there were also some devices that had an overflow in their counter, and they calculated the leap second had started when it hadn't started. Switch boundary clocks. A lot of switch vendors are building boundary clocks into their switches. It's not as simple as it might appear at first, and there are a lot of problems with it. So sometimes you'll see boundary clocks that don't pass the right data or don't synchronize properly. And this last one, we had a customer with 2 data centers connected by a high-speed WAN. They were told it was perfectly symmetrical. Now, asymmetry is the bane of time synchronization, right? If you don't have a way to measure how long a packet took to get to you, what you have to do is you have to say, in my handshake, I started the timer, I sent out a request, I got a response, and I divide by 2, or I do something to try and estimate how long that was. If the path is asymmetric, if it takes significantly longer for it to go one way than the other way, your calculation of time will be off, and there's really no way to recover from it. In fact, it's a basic mathematical problem of 2 unknowns and 1 equation, right? There's just no way to get around it. So, but if you have 2 GPS clocks on both sides, and you're doing measurements, and you're counting the 2 different time sources against each other, you can see that the one is offset from the other, and you can immediately confront it, even if your networking staff swears up and down that that's not happening. Some other failures that we've seen, lightning strikes. Lightning seems to love GPS antennas for some reason. NTPD servers changing sources, broken clocks, bad oscillator. I mean, I don't want to say anything bad about GPS clocks, but equipment does break. GPS spoofing and jamming are more common than people think it is. Misconfigured routers and switches is a big problem. Terrestrial PTP sources are a great thing. We love those, but they can also fail. They're not always accurate. You want to be able to cross-check them too. And lost PTP multicast and switch restarts, it's a big issue, right? I mean, PTP multicast is a stateful protocol. And when your switches fail and come back up, they lose information about what state they were in, and you may just fail to operate. So failures are more common than we expected, especially jamming. We hadn't really had the idea that how common jamming is. But you can buy a GPS jammer for $20 on the internet, even though they're illegal everywhere. And people do buy them. And a lot of truckers have them to keep their bosses from following them. Right? So there are problems that happen all over the world where some guy is taking a nap and he turns on his GPS jammer so that nobody back in the office is seeing that his truck isn't moving. And there's no GPS reception anywhere around him for cheap signal. So that's an interesting issue. We also found out when you bring in fault tolerance and multi-source comparisons, you'll find out that a lot of systems that were presumed to be working were not. And it's, people talk about how this new standard, the 50 millisecond standard, doesn't really get us all the way we want to get. But there are a lot of firms out there who are not meeting the old 1 second standard and think they are, right? Timing is really hard to measure. If you just have a watch and the watch says it's 12 noon and you believe it, you may or may not be right? It's just one clock. So you have to have multiple clocks to compare. I'm going to skip over this one. I'm going to show you a map. How much time do I have left? Okay, great. Okay, so what we also added to the system was, we built in a lot of diagnostics. And here's a diagnostic that shows you what's called a time map. And you can see a source, where it's getting its time from multiple sources at the top, where they're getting their time from. It traces back as far as it can get. And you can see up at the top, that little telephone protocol is the old ACT protocol that NIST still has. So there are some sources there that were claiming to be high-precision sources, but they're actually going over a modem back to Colorado Springs. The green lines there are PTP. We're distributing PTP from the source. The red lines are NTP. The length of the lines corresponds to our estimated one-way delay. So this gives you a lot of information, and actually, if you're operating a big network, and again, this is a difference from the telco networks. The commercial networks in banks and in large financial institutions are incredibly complex, huge networks with enormous amount of cross-connection. A map like this really helps you diagnose what's going on or why it's going on. So these kinds of visual tools are a lot more important, perhaps, than people recognize. This is my supposedly independent sources that we're not. You can find. Another diagnostic that we have developed that we thought we ended up having to do is a heat map for what your GPS antenna is seeing. And this is kind of if you're lying on the roof looking up at those satellites from your GPS antenna. And the heat map is showing you have really excellent quality where it's yellow, the brighter colors and the darker colors are less good quality. And you can see the dots of the GPS moving across it. And again, what we found is time really was considered an arcane kind of special, what people in the industry say a want to have, not a must have. And so a lot of places have GPS antennas or GPS systems that are not that well set up and not monitored. There's all sorts of interesting financial issues having to do with GPS clocks, because sometimes you have 5 or 6 different companies before you get between the data center and the roof, and they're each negotiating a deal with the other one. And you run into all sorts of kind of interesting issues when you see this. Here's an example of something. We did a monitoring in New Mexico. White Sands, of course, is big military base, and they do tests of GPS jamming. And you can see here, this is like a source that's getting jamming now on both sides, in both directions. I'm going to show you a slide as well. Oh, this is a nice one. This is LD4 in London. There was a problem there that went on for months and months where people were saying they were getting intermittent bad GPS. The diagnostic showed that at certain times during the day, you would go from something that looked decent like this to something that became all dark. Okay, and so I'm going to show you. Hopefully, wait a second. How do I go back? Is that my? This is supposed to actually be a movie. I guess we're not getting to see it. Oh well, unfortunately, there's no way to click on it or something. It worked before. So all right. Anyway, if it was running, it would show you that that little purple area in the corner grows out. The little purple area in the corner grows out and becomes and covers the whole thing. And it turned out that what had happened there was they had over the years added more and more GPS antennas onto the rooftop. And they had one of them turned out to be bad, and every now and then it was kind of starting to send out noise signals, and everything was getting just way too much feedback in it, and nobody would be able to get time for a while. And eventually somebody went up on the roof and diagnosed what the part was. But that kind of diagnostic is something that you really need, and it's a great mixture of a technical and a business problem, because for many of these systems, like I said, you have multiple different companies between the rooftop and the data center, and they all want to blame each other for any problem that you see. So this kind of thing says, well, look, I'm looking out on the roof. Here's what the GPS antenna sees, and there's a dark spot over there. And we've seen this error. I mean, the other really interesting thing is, because there's been so much construction in Chicago, we have repeatedly diagnosed problems where people are going, this used to work, what's wrong with it? And what's great about, of course, GPS is it gives you position as well as time. And this system is hooked up to Google Maps, and then you go look at the rooftop. You go, there's a skyscraper over on this side where there was a vacant lot last month, so that's why you're not getting time over there, because there's a building in the way. So anyway, that kind of diagnostic is really very useful. So I'm going to summarize what the approach is. We're time protocol agnostic. We want to do PTP, PTP telecom, NTP, pulse per second, bus cars. They're all different sources. We want to be able to mix and match and build up for as much resilience as possible. Multiple sources are essential for fault tolerance and for security. There's really no difference between a fault caused by some error in the system and a fault caused deliberately, and you want to be able to guard against both of those. They show up the same way. You want to be able to document, especially for regulators, that you have multiple time sources and they all agree with each other. So you did your due diligence. You're not just saying, I said it was 12 o'clock because, I had this clock. It told me it was 12 o'clock. You're able to say, I cross-correlate these clocks and they all work. And then it's the intelligence in the client and the slave. The time consumer has information and analytics that's not available to your time source. Your time source is sitting over on one side of the network, or maybe may not even be that far away, but you have a very complex network that's carrying those time packets over to your time client. And the time client is where you need to locate the intelligence, because it's using that information, and it needs to validate the information. So that's the quick thing. I've got questions. We have time for questions? No questions?
No, we got one.
Okay. Oh.
Hey, thanks. Hi, Pedro Estrela from IMC Financial Markets. Completely agreed that multiple sources are regarded as slaves. Completely agreed that then a typical fault or an attack, it's all the same thing, the solution. Based on your experience, what will be the minimum steps to fix this in PTP, in the standard?
We're not really involved in the PTP standards committee, although you and other people have suggested we should be, and probably we should be. But looking at the enterprise standard, I can see that they're adding capabilities to do failover. They're adding the capability to look at multiple domains and go from one to another one, which I think is really an excellent thing. We like to be able to also fail over to NTP sources as well. But I think this is being addressed. It's not particularly easy technology, because everything is, as I'm pretty sure, because everything is in flight, and you don't really know. You don't want to fail over incorrectly. That's a serious and easy error to make. But yeah, I think the standard is going to have to come to grips with that. And you can see, just from my point of view, looking at the draft, the IET draft, they're kind of tiptoeing around. How do we get around this BMC that tells us we have to follow what the source says and try to use more sense about what we follow? So I think they're moving in that direction, and I appreciate your advice that we look at it more closely. So what else? Anything else? Any questions? No questions? Okay. What? Oh, I'm going to show the last slide. Yeah, sorry. Wait, I want to show the next one. Wait, where is my last slide? Oh, here it is. Okay, I have actually a better slide, but this is a good one, and I thought I'd show because of Dr. Levine's remarks. This is the 2015 leaps. This is the 2015 leap second, and you can see at the top This is a year ago. I have another slide for the 2016, but it's not on this deck. You can see at the top, you can see Google sliding off, right? Google had this bizarre idea that they would take, they took 24 hours then. This year they took 20 hours. They have a really nice slide. You can show them. And so what they'll do is they'll slide off, and you can see during the time, all the other NTP servers, they're generally okay, except for the ones that, were overeager and jumped early. But, Google slides off, and then everybody switches. Or most of them do a switch, or they do a short slew. Our stuff does a slew over 5 minutes normally. But there's a sort of a period of confusion, and then Google is still a half a second off, kind of coming back into accuracy, and everybody else has moved on from it. But the leap second is this cataclysmic event that we have to deal with every now and then. But the point that I wanted to make from it is, if you had a single source, and your single source was Google, or it was following Google, or it had been programmed incorrectly to do that, you would slide off of the time for a whole day and not know that you'd slid off the time. And that's the issue with multiple time sources. Okay, thank you.